In last lecture, we have started with the latches, and in that, the RS and D latch, those two concepts we have seen. And after that, we have gone for another concept which is called as gated latches. And there we have seen if the gate input, that is the enable input, is active, then and then only the input that will get traveled towards the output. But if the enable input is 0, then whatever may be your input, that will not get transferred towards the output of that latch. And that's why we have commented in last lecture that the latch circuits are not suitable for being the synchronous logic circuits. Because here, as per the enable signal status, the excitation inputs will be given as an output Q value. But this will be having a problem in changing the output as per the change in input values. And so we have to go for applying a special timing control signal which is called as a clock instead of the enable input for the latches. And when we are working with respect to this special timing control signal clock, at that time, that memory element will be now said to be the flip-flop parameter. And these flip-flops in today's lecture we are going to deal with. And generally, as already marked out, these flip-flops are the age-triggered memory elements. So we are starting with first type of flip-flop. Flip-flop title is SR flip-flop, and I told you in last lectures also that whatever the title of that latch or flip-flop will be there, that title will consist of how many number of inputs are acting for that flip-flop or latch. For example, if I am saying it is D latch or D flip-flop, only one input D will be acting for that flip-flop or latch operation. Similarly, if I am saying JK or SR flip-flop or latch, then there will be presence of JK or SR as an input for that latch or flip-flop. But the basic difference between the flip-flop and latch lies in having the triggering method and having a control signal name. Latches will be having the control signal which is named as an enable or gated input, while the flip-flops will have a control signal which is named as a clock parameter. Again, the latches will be the level triggered memory elements, while flip-flops will be the age triggered memory elements. So these all basic differences also we have covered in the last lecture. But once again, to remind you the difference between these two things, I have revised these. So here I was telling that based on the input value condition, either of the stable state that we are going to obtain. So regarding the set state, we have mentioned that to have a set state to be obtained from the flip-flop, we should have the S input to be 1 or it should be high. And so I was saying that either of the state will be obtained as a stable state output, and there for having the set state and for having the reset state, the input conditions have been mentioned in this. So if you are observing this characteristic table that I have mentioned on the slide, that has been mentioned for positive age-triggered SR flip-flop. And that's why here, if you are observing in the column of the clock, I have shown the upgoing arrow. the upgoing arrow will indicate that the clock is positive age triggered clock. So whenever the upgoing arrow will be indicated in the column of clock, you have to understand that that flip-flop is a positive age triggered flip-flop. But if suppose the below going arrow is indicated, it means that it is a negative age triggered flip-flop. It is a negative age triggered flip-flop. But here all the arrows are indicated upward. So I am saying that this flip-flop is a positive age triggered flip-flop. So with change in the applied inputs of S and R with the clock which is rising age clock or positive age triggered clock, we are seeing here that the next state which is indicated by Q of t plus 1 has been changed. So let's go for this characteristic table understanding. Here we are observing that both S and R inputs are 0 and clock we have indicated as don't care condition. That means for the clock, whether you will be having either positive age trigger, negative age trigger, high level or low level. Whatever may be the state of your clock signal. It doesn't matter for providing the Q output. Whatever may be the clock value, but if both flip-flop inputs are 0 as S and R, then here the next state of the Q will be the previous state only. That means we can comment that when the clock is not considered but S and R inputs are 0, in the flip-flop state, no change will happen. In the flip-flop state, no change will happen. The next input condition is when S input is 0 and the R input is 1. So let's check here that S input is low and R input is 1. And along with that, we are having positive age to be occurring for the clock. And if this is all input conditions, then and then only the flip-flop will go to the reset state. And to indicate the reset state, the next state value should be 0. The next state value should be 0. On the contrary, now if the S input is 1 and R input is 0, along with that we are having a age which is occurring as a positive age for the clock, then and then only with this above statement we are saying that our flip-flop is going into the set state, and that set state will be indicated by providing the next state value as a 1. By providing the next state value as a 1. But now the remaining combination for the input is what? 1, 1. So with respect to this 1, 1 input combination, if my clock age is positive age, then here the next state will be invalid state. And that's why here the question mark has been indicated. So the table in which we are indicating the input value combination along with the enable signal or the clock signal, and we are commenting for the next state value of the flip-flop, that table is said to be the characteristic table. Because in combinational circuit, we were putting out the combinations of all input corresponding to all possible input combinations, what will be the output, and that particular table we have marked or named as a truth table. But in case of the flip-flop, when we are commenting for the next state value to be obtained with respect to the present input and the control signal conditions, that table will be named as characteristic table. So please remember the changes with respect to the combinational circuit and the sequential circuits. Now, we will go for the basic flip-flop representation in terms of the gate that we see. And that's why this will be also said to be the NAND gate representation for the SR flip-flop, wherein we can see that in this total circuit, we are having three basic parts. One is said to be the NAND latch, second one is said to be the pulse steering circuit, and third one is said to be pulse transition detector or the edge detector circuit. Now, what is task of each of that component in the flip-flop operation? That in detail we are going to see. But whenever the flip-flops will be represented in terms of a gate circuitry, that time you will be having these three basic circuit parts which I have mentioned over here. And in that representation, sometimes we are having, instead of that NAND gate, the NOR gate also to be used. So SR flip-flop will be represented in the form of a NAND gate or a NOR gate also. But on this slide, I am presenting the SR flip-flop in form of a NAND gate. And as the name mentioned for this component, it is going to act as a latch. Latch means it is going to simply transfer the value when there will be the control signal that has been enabled. The next part of the circuit is a pulse steering circuit. So whatever this bubbled OR gate you are observing after this NAND gate, that bubbled OR circuitry part is said to be the pulse steering circuit. This pulse steering circuit is going to give the direction to the input. That means whether it has to be transferred towards the output or it has been holded for one clock period until the change in the clock age is going to happen, that decision is taken by this pulse steering circuit. While the third component that we have marked is pulse transition detector or edge detector circuit, which is present as an input for this NAND circuitry. So here in the diagram, you can see that the clock, which is a control signal, that will be provided to this pulse transition detector. Because in previous description, I told you that this is a positive edge triggered flip-flop. So in the clock, the transition of this pulse has to be detected. And that transition should be detected to understand when this clock is having a positive edge or having a negative edge. Because with respect to positive edge only or with respect to negative edge only, the output of the flip-flop has to be changed as they are acting as a control signal. And that's why initially here only the pulse transition detector circuit has been placed. Now, whatever the pulse transition circuit, that will be provided over here. And whenever the positive edge will come to here, that means that value is 1 for the NAND gates, one of the inputs. Along with that, to these NAND gates, separately we have connected S and R inputs. So here S input for first NAND gate and R input for the second NAND gate has been connected. We know that when both the inputs for the NAND gate will be same, we are going to obtain the zero output for. And with this principle, if I am finding this S value as a 1 and positive edge triggered is happening, the upper NAND gate output will be 0. But when this lower R input is 1 along with the positive clock, then the lower NAND gate will produce the output as 0. So this is how when the S input will be gate will produce 0 output, and when R input is 1, the lower NAND gate will produce the 0. So here we have seen the conditions when the NAND gate outputs will be produced as 0. Let's check for this bubbled OR gate output and their steering, how they are providing the outputs or how they are going to generate the. So in this case, what we are observing is if the 0 output for the upper NAND gate is produced when S input is 1 and the clock is a positive clock, this 0 will be bubbled at the input side, so it will get 1. So 1 is provided to this OR gate. At that time, whatever the previous Q bar output is there, let's consider this as a Q bar output. That Q bar output will get bubbled again, and these two bubbled inputs will get OR to produce this Q. So this is called as a cross-coupled NOR gate circuitry, bubbled OR gate circuitry. In this part, here you can observe that I have made two parts. One part is indicating the positive going transition, that is rising edge transition, and another one is showing the negative going edge transition. And here purposefully I have shown the signals which are generated by these NAND gates. So here clock will be given as an input. Then the inversion has been done, which is indicated as a clock dash signal. And this original clock and this inverted clock has been provided to the ending circuitry, and that signal we have marked as a clock star. So what will be the clock star output that we are going to check here? So let's say the clock signal is having this like a square wave representation. So clock dash will have exactly opposite outputs, but as for the clock dash to be generated, that clock signal has to travel from this inverter, and that inverter traveling will produce some delay in the transition of that signal. And that's why here the edge, which is positive edge for the clock signal, that will be reflected in the clock dash as a negative going edge after this much of the delay, which has been marked from this vertical dotted line. So this will be the transition delay caused by this NOT gate. And that's why in the clock dash to be obtained, immediately after getting the clock signal to be high edge, we are not going to get the negative edge to be appeared for that clock dash signal. Now, when this delay is going to happen, at that delay, at the output of this AND gate, we are going to observe this small pulse, which is called as a glitch in the flip-flop, which is called as a glitch in the flip-flop. And these glitches are caused due to the transition delay occurring in sequential gates which are connected in the flip-flop circuitry. And that is what the drawback when we are implementing these gates as a flip-flop, that the glitch generations are present into the circuit due to the transition of the transition delay of the outputs from one gate circuitry to the another gate circuit. In the same case here, you can observe for negative going transition. So in the negative going transition, considering here that as it is a negative going transition, so this AND gate inputs will now get bubbled. That is what the change in the circuitry to get the negative going transition. Again, we are starting with the clock signal. clock dash we are obtaining. But after getting the clock dash here, at the input of that AND gate, we are having inversion itself. So we are observing that delay when the age is going to change from the low level to the high level. And during that period here, we are observing the glitch generation into this clock star signal. So this is said to be the glitches generation which are going to hamper the circuit behavior, and those are the things which are unwanted into the further digital circuit operations.
Yes, ma'am.
Okay, fine. So I'm moving with the next flip-flop, which is D flip-flop. So as told, the name indicates the number of inputs. So in the name we are having only D. So D will be a single input for that flip-flop. So with respect to this D input, with the clock age condition, we are going to observe the change in the next state of the flip-flop. As a single input is present, so that input may be either high or low. And with respect to that input as either high or low, we are going to get two stable states of set and reset. But generally, in D flip-flop, we are saying that always the Q output is going to follow the D input with the clock age. And to convert the SR flip-flop into the form of a D flip-flop, we have to add an inverter for this R input to be connected, because we have to get a single input to be obtained from the basic SR flip-flop, which is having two input condition. And that's why if you are observing in this block diagram, basically this block is of SR flip-flop with the clock control input that has been shown, but we have to convert this SR flip-flop in form of a D flip-flop, which is having a single input. And that's why you are seeing here that the D input has got connected to S, and here the D input has got inverted, and that inverted input we are connecting to the R input of this SR flip-flop. Because we are saying that in D flip-flop, always the Q state or Q output is going to follow the D input with respect to the clock age. And that's why in the truth table, now you can observe for the positive age triggered D flip-flop itself, because I have shown here the clocks which are with the upgoing arrows, and D will be either having the input value as 1 or 0. So if D is 1 with positive clock age, then the next state will be definitely with one value, which is said to be the set state for the D flip-flop. While if the D value is 0 with upgoing clock age, which is indicating positive age trigger, the next state will be 0 as the D input is 0, and this state will be said to be the reset state. This is how we can get the conversion of positive age triggered SR flip-flop in the form of the D flip-flop. So let's check now, if we are saying that the output for the D flip-flop always follows the input value of D, then what's its application? So generally, this D flip-flop will be used for parallel data transfer. So here I have presented one diagram wherein you can observe the combinational logic circuit is present, and for the combinational logic circuit, three outputs have got generated, and these three outputs we have marked as a X, Y, Z. And here, with the help of these three different D flip-flops separately. This X, Y and Z will be provided as an input to the next coming input circuitry. So to separate out this and to transfer the data parallelly, the D flip-flops can be used on as shown in this diagram. But we are knowing that here the D flip-flops are going to work with respect to the clock edges. And if you are observing, for this clock edge, the mark has been given, which is the downwards mark, and from that downwards mark, you have to understand that these D flip-flops are the negative going transition based D flip-flops. And that's how here you can get the discrimination to be done in the operation of positive edge triggered base or negative edge triggered base flip-flop parameters. Now, the next flip-flop that we are going to see is a JK flip-flop. So as I have mentioned in the SR flip-flop, again here we are having three parts. One is the pulse steering circuit, second one is the pulse detector circuit, and third one is the NAND latch. So with the three components itself, now this JK flip-flop operation we are going to check. Only what is going to change is in SR flip-flop, the inputs were S and R, while here the inputs will be J and K. In this case, we are not having the invalid state presence. That is the basic difference in SR flip-flop and the JK flip-flop. In case of the SR flip-flop, when both the inputs are high, that state we have marked as an invalid state. But in case of a JK flip-flop, no any invalid state will be existing. Rather than that, that state will be named to be the toggle state. So JK flip-flop will be having basically two stable states with the toggling mode of operation when we are having both J and K inputs as one value. So here I have mentioned that table with J value as a high and K value as low. That state of the flip-flop will be said to be the set state, while K value as a 1 and J value as a 0, that state will be marked as a reset state. But if suppose both the inputs J and K are 0, that means they are low, then the previous state will be continued as a next state, which is said to be no change in the next state. But as already I have mentioned, when both the inputs J and K will be high, that state will be mentioned as a toggle state. Now we will understand how this state and the three basic components for that circuitry are going to work. So here you can observe, instead of S and R inputs, J and K inputs are present. The clock signal has been given to the pulse transition detector, then the NAND gates, and after that bubbled OR gate, which are cross-coupled bubbled OR gates that has been mentioned, which we are seeing that the pulse steering. So if you are observing the previous diagram for SR flip-flop and JK flip-flop, the change what we are observing is only in case of the inputs. And here we are seeing that the J input when sets, J input is 1, it will set the flip-flop, and when the K input is 1, it will get the resetting of the flip-flop. So here the characteristic table has been presented. So as mentioned in the characteristic table, we are going to comment for what is the value of the next state based on the present input conditions and the control signal parameter. So here we are operating with positive edge triggered control signal. That's why for the clock again we have shown upgoing arrows. These will indicate the positive edge triggering value. So if J and K inputs both are 0, the next state will be the present state only. So here Q of t plus 1 we have indicated as Q of t with the comment that no change in the output state is going to happen. But if J is 0, K is 1 with the positive edge triggered clock, then the next state will be definitely having magnitude as 0 with the condition of resetting of the flip-flop. But if J is 1 with K value is 0 with positive edge trigger, the next state for the flip-flop will be the set state with the output value as 1. While now, as the last input combination of J and K as 1, 1, you are observing here that it has been mentioned as Q T dash. That means continuously it will go on changing from 0 to 1 and 1 in 0 level. And that's why this state is called to be the toggle state. But in case of the SR flip-flop, when both S and R inputs were 1, we have said that as an invalid state, which is not true for the JK flip-flop. With the condition of both the inputs of 1, that will be set the toggle state of operation. So here, with the 3 input conditions of the present state and present input combinations, the next state have been mentioned over here. If say my present state is 0, so with that present state to be 0, J and K will be having 4 possible input combinations as 0, 0, 0, 1, 1, 0 and 1, 1. Similarly, if I am having present output state as a 1, with respect to that also, both JK will have the input combinations to be changed again as 0, 0, 0, 1, 1, 0 and 1, 1. And that's why in this input side column of the characteristic table representation, we are finding out totally 8 number of input combinations. And based on that present state value and the present input value for these all 8 possible input combinations, we are commenting for what will be the next state. And that has been presented into this column of Q of t plus 1. So if I am having present state at 0 and both inputs are 0, we are saying that there will be no change in the next state. So next state, that is Q of t plus 1, will be Q of t. And that's why here in the first row, the Q of t1, t plus 1 value has become as 0. Now, we will move towards the next condition in which the present output state is 0 and the input conditions with J as 0 and K as. So we know when J is 0, that time the flip-flop will be in reset condition. And for the flip-flops to be in reset condition, next state value should be 0. And that's why the Q of t plus 1 will be equal to t. Now, the next input combination of J is 1 and K equal to 0. This present output is 0, but as J value is 1, which will drive this flip-flop into the set condition, and that's why here the output of Q of t plus 1, that is next state, will be 1. The next condition is that when the present output is 0 and both J and K are 1. we have said that when both j and k are 1, the q of t plus 1 is qt dash, and qt value is 0, so qt dash will be 1. So here we are seeing the toggling from the 0 level to the 1 level. That's why we are saying this as change from qt to qt dash. With the next condition of q value as a 1 and present inputs are 0, 0. So no state change will occur. So qt plus 1 will be 1 as it is. In the next condition, j is 0. J0 causes the flip-flop to be in reset mode. So whatever may be your present output state, but J being 0 causes the flip-flop to be in reset mode. So this Q of t plus 1 will become as 0. In the next condition, J is 1. J is 1 is always driving your flip-flop into the set mode. So whatever may be your present output, that will not get impacted on this change value of this Q of t plus 1. So this being J equal to 1 will drive this next state to the set state only. Let's go for this last condition, which is saying that both J and K are 1 with the present state to be 1, then with 1, 1 condition for both inputs. In the next state, the toggling output we are going to get, which will reflect to be as 0 as the present state value is 1. So this is how this table, which is said to be the characteristic table, that has been written with the help of this truth table of the JK flip-flop. Now, if I will represent this characteristic table in form of a K-map, which is of 3 variable K-map. So by representing this characteristic table in form of a K-map of 3 variable, and by getting simplification to be done, I can get the characteristic equation which is mentioned for Q of t plus 1. And that characteristic equation from the K-map of this table will be obtained as Q of t plus 1 is equal to J Q dash plus K dash Q. For that, here the 3 variable K-map has to be represented and get the simplification of that K-map to be done for this characteristic table that we have presented over here. So you will get the output equation for next state Q of t plus 1 as JQ dash plus K dash Q. So this equation is said to be the characteristic equation for the JK flip-flop.
No, ma'am.
Because if you are able to understand in the characteristic table and the truth table of this flip-flop, then only in VLSI subject you will able to design the digital circuitries. Is it understood? Okay. I will go for the next flip-flop, that is T flip-flop. This T flip-flop here, I was telling regarding the next flip-flop, which is T flip-flop. And T flip-flop is nothing but the single input version of the JK flip-flop. As like we have converted the SR flip-flop to D flip-flop, here the JK flip-flop we are going to convert to the T flip-flop. But to convert from the SR flip-flop to D flip-flop, the R input we have get inverted. But here to get the T input, the K input we are not going to have to be applied with the inversion value. Simply we are going to get the plugging of J and K together, and that will be provided as a T input. So here you can observe that the JK flip-flop diagram in terms of three components of pulse transition circuit, pulse steering circuit, and the input that has been presented over here, where you can observe that for the two NAND gates, previously we were having inputs at J and K, but I have told to convert the JK flip-flop to the T flip-flop, only we are going to tag the two inputs together as J and K to form the T inputs. And that's why here to these two NAND gates you are observing that this tagging of one of the inputs of that NAND gate has happened and that has been named as a T. While another input for those two NAND gates will be coming from the pulse transition detector circuit. And to that pulse transition detector circuit, this clock input has been provided. So in this case, we are going to see that J and K inputs are tied together. And as it is having only one input, so for one input, two possible conditions of values will be there with 0 and 1, as this is a digital input. Again, we are referring with the positive edge triggered flip-flop. So clocks have been indicated with the rising arrow to be presented. Now, as we are saying, this is a toggle flip-flop, and that's why either that flip-flop output will be in getting the toggling output or it will be having no toggling output. And that two states which are stable states to be obtained from this flip-flop based on the input condition of T at 0 or 1. If the input T value is 0, then the next state for that flip-flop is not going to change. It will remain as it is, whatever the present state is there. But if the T input is 1 with the rising edge clock, then whatever the previous state is there, that will get complemented. That means here the toggle state will occur. So in short, we can say that whenever the T input is 1, that time only the toggling state will be obtained for this flip-flop to be. But when the T input is 0, there will be no any change in the output of the circuit or the next state of the flip-flop circuit. Now, as like the JK flip-flop here, again we are going to obtain the characteristic equation for the T flip-flop. But to get the characteristic equation, we have to first mention the characteristic table. And in the characteristic table, the inputs will be the input of the flip-flop and the present state, while the output column for the table will indicate the next state of that flip-flop. And here we are representing now the present state as a Q and next state as Q of T plus 1. While this flip-flop will have only one input, that is T. So we are presenting here Q and T into the input side columns and Q of T plus 1 in the output side column. So Q, that is present state, will be either 0 or 1. But with present state to be either 0 or 1, the T may be 0 or 1. And that's how here totally 4 possible input combinations we are going to obtain. So we have said that if suppose the T input is 0, there is no any change in the next state. And that's why here you are observing when T is 0, whatever the Q state is there, that has been reflected as Q of T plus 1. In both cases when T is 0. So here the present state was 0, it has been reflected, and here the present state was 1, that has been represented for Q of T plus 1. But if the T input is 1, then the present state will get complemented for the next state representation. So that you can observe in the second row and in the fourth row of this table. From this again, by representing a two variable representation here, you can observe that q of t plus 1 is going to be obtained as t q dash plus t dash q, which is said to be a characteristic equation for this T flip-flop. So generally in the digital circuit designs, for the state machine representations as well as for getting the design of the circuitries to be done, basically the characteristic table of the flip-flops are used in those parts, and that's why here for these basic flip-flops of JK, RS and T, we have seen this characteristic table and the characteristic equation. So in the next part of our lecture, we are going for how these characteristic table will be used in the designing and getting the state tables and state transitions to be represented. So here friends, you can see the application of the T flip-flop. D flip-flop, we have said that it is applied for getting only the parallel data transfer to be done, while this T flip-flop will be used for the frequency division operation. When I am having a single T flip-flop, that single T flip-flop will give me the output which is divided by 2. So that is said to be divide clock frequency by 2. So here in this waveform representation, you can see that the clock is positive edge triggered clock. At that clock, I am finding that the Q has got changed. As this particular flip-flop we have said to be the positive edge triggered flip-flop, and that flip-flop is in set mode. This set mode will be persistent until and unless the next positive edge trigger in the clock is going to happen with the change in the applied input. So in this instant, when the next positive edge trigger has happened, if the T input has got 0, then this particular state change is going to happen. So here you can see that with respect to this clock, in the Q, only a single transition has been obtained. While in the clock, we are having this one transition and this as another transition. So which is seen to be the divide by 2 number of transitions for the Q output. And that's why we are saying that this T flip-flop is going to give us output which is a divide clock frequency by. But if suppose as like this, the number of T flip-flops in series I am going to connect. In series means the first T flip-flop output I am going to provide as a clock input to the next T flip-flop. Then as many number of flip-flops I am connecting, for each of the flip-flop, the extra divide by 2 clock frequency will be obtained. So here you are observing the example where I have connected 2 T flip-flops in series in such a way that the first flip-flop's Q output I have connected to the clock input of next flip-flop. Then for first flip-flop, it will give divide by 2 output which is represented by this QA, and this QA will be given to the clock, and this QA will be again having divided by 2 which is represented by this QB waveform. So totally divide by 4 output we are going to get for the QB output parameter. So this is how we can observe that if in series I am going to connect the T flip-flops then we can find every T flip-flop is responsible to give extra division by 2 value. Extra division for the frequency by 2 value. And this will be used in the counters, which we are going to see in the next chapter. So these are the applications for the T flip-flop. So in next lecture, we are going to see for the concept of asynchronous inputs, that means preset and clear based flip-flops, and after that we are going for the state machines to be observed. So here today I am going to stop. If you are having any doubts, you can post me that in the chat window, or by unmuting yourself, you can ask me until I will post you